Solving first order PDEs. There are various ways of solving PDEs. For instance, if we have the PDE u sub x being equal to 0, then integrating with respect to x and holding y constant, we get the solution uxy being equal to a function that depends on y. Then also, if we have u sub y being equal to 0, then we get a solution that is a function of x. What if we have a PDE of the form a u sub x plus b u sub y equals 0? Let us write the inner product of this. So we get a comma b dot u sub x comma u sub y being equal to 0. Now let v be equal to the vector ab. Then we have the vector v dot, then we have the vector a, then we have the vector ab dot nabla u being equal to 0. That is, the PDE, we're able to write the PDE as a directional derivative of u in the direction of v being equal to 0. What's the meaning of this? Let's first of all sketch the vector v. So we have the ij direction, so let this be our I direction and this be our j direction. Then the vector v, from any point we move a unit along the I direction, then b unit along the j direction. So we have the vector having this is our vector function v being equal to ai plus bj. Now the directional derivative being equal to 0, the directional derivative of this being equal to 0 means that the solution to the PDE is constant in the direction of the vector v, meaning that that solution depends on a function that is parallel to the vector v. So all functions that are parallel to the vector v will have our solution of the PDE depending on those functions, and all functions that are parallel to this vector has this equation: bx minus ay equals c, because this is having a positive slope and all the functions that are parallel to this vector must also have positive slopes. And if you make y the subject over here, you get our slope being equal to b over a, which is positive. So we are saying that, or we have realized that the solution of the PDE is a function of, or is a function that depends on bx minus ay. Now these curves or these lines are called characteristic lines of our PDE. Characteristics lines. So now let's take one example. So here is our very first example. We are solving for u sub x minus 3u sub y being equal to 0. So we have our a to be equal to 4, and we have b to be equal to negative 3. Then the solution to the PDE is given by a function that depends on minus 3x minus 4y. Now applying the IC, we get u0 of y to be equal to y cubed. So we get our y cubed now to be equal to, wherever we see x, we put 0. So f of negative 4y. Now we can transform this to, let's say we have p be equal to minus 4y, then y will be equal to minus p over 4. Then f of p will now be equal to minus p cubed over 4 cubed, which is 64. So we have our solution, particular solution uxy being equal to 3x plus 4y all cubed over 64. So wherever we see, we are substituting this into the p, and we simplify to get this as a solution of the given PDE. Now let's take the next example. So over here we have let our a to be equal to 3 and b to be equal to 1. So we have our solution u of x or uxy being equal to a function that depends on x minus 3t. Now applying the conditions, we get u x0 being equal to, this is t, ux0 being equal to f of x. So we get sine x being equal to f of x. So now our particular solution becomes u of xt being equal to sine x minus 3t. So wherever we see x, we put x minus 3t over here. because f of x equals sine x. So f of x minus 3t will be equal to sine x minus 3t. Now let's consider another method called the coordinate method. The coordinate method aims at reducing the PDE to an ODE. Then we use known methods to solve the obtained PDE. So we are still looking at how to solve a u sub x plus b u sub y equals 0. So earlier on, we've seen that the directional derivative vanishes along the vector v a b. So we make change of variable such that the new x-axis will be parallel to the vector ab. Then the y will be parallel to the vector b minus a. So now we have this being our new axis. So let this one be our z axis and this be our eta axis. So this will be equal to xy dot ab. Then we have this being equal to xy dot b minus a. So these two vectors are orthogonal. Now we need to form a PDE in our new variables. So we are going to have our u being a function of z and eta, then eta being a function of x and y. The same thing applies to this, also being a function of x and y. So now we are going to apply the chain rule to obtain our PDE. So the chain rule, we are going to get u eta y, then we have eta x over here, then we have z, we have u z, then we have z x over here. So we simplify this further to obtain ax plus by, then over here we get bx minus ay. So we realize that eta x will be equal to b, then eta y will be equal to negative a, then we have z x will be equal to a, then z y or zx zy will be equal to b. So now we'll find our partial derivatives. So u x will be equal to u z x plus u eta x. So we get the following. Upon simplification, this will give us a, then this will also give us b. Then we have our u y being equal to u z y plus u eta y. So we simplify this to get u z b plus u eta, then minus a. So now we substitute this into our ODE, our partial derivative, into our PDE to obtain a into u zb, uza, then plus u eta b, then plus b into u eta b uzb, then plus u eta negative a. So now this is equal to 0. We simplify this now to get a squared u z plus ab u eta. Then now we have plus b squared u z minus ab u eta being equal to 0. So we simplify this to get a squared plus b squared u z being equal to 0. Now because this is not equal to 0, a squared plus b squared is not equal to 0, so we divide through to get u z being equal to 0. So we have written our PDE into a new coordinate. We have reduced the PDE to an ODE. Now we can solve this by direct integration. So we have u being equal to a function of neta, but we know neta is equal to bx minus ay. So we have our u now being equal to f of bx minus ay. So this was the solution that we've seen earlier on.